5.5, Trapezoidal Rule. Okay, this is the last section of the chapter, and it's going to circle back to what we were doing at the very beginning of the chapter, finding the area under the curve using rectangles. Well, this is finding the area under the curve using trapezoids. Okay, so I put a quick review from the first part of the chapter in here where we were doing Riemann sums, section 1 and 2. So we had the right rectangular approximation method or the left rectangular approximation method. And here the subscript 3 means we're going to use 3 rectangles. Okay, so here we have our curve, just a basic parabola, y equals x squared, on the interval from x being 0 to x being 3. So I drew a picture 0 to 3 of my parabola down here. And if we're going to do the right side, that means we use the right endpoints for the height of our rectangles. Let's see if I can draw these in. Oops, this tool. Okay, so if I look from 0 to 1 in that interval right there, I look to the right side, which is the height of my function at 1, and I draw my rectangle in straight across. Well, somewhat straight. Okay, and then I go to the area between 1 and 2, and I go, oh, not sure what's going on there. Here we go. Okay, so at 2, I go straight across, and I get that height for my second rectangle. And then on the interval 2 to 3, I take the right side there and go straight across, not real straight. And these would be my 3 rectangles. So I'm using the height at 1, the height at 2, and the height at 3. So for a rectangle, it's length times width. We have the length of it is delta x. That's going to be 1 for the width of each of the rectangles. And the length or the height of the rectangle would be f of 1, then f of 2, then f of 3. So the difference, of course, being if I'm on the left side, then I use the height at 0 for my first rectangle, which means I have no area. The height at 1, for the length at height at my second rectangle, and 2, the height at 2 for my third rectangle. So instead of going f of 1, f of 2, f of 3, it's f of 0, f of 1, and f of 2. And I plug in what those numbers are, and of course, if I'm doing the right method here, I get a larger number, 14, compared to if I do the left side, which is 5. Okay, so the actual area that's going to be between, or excuse me, be underneath the curve of our parabola, the actual exact area is somewhere between 14 and 5. And so then the question would be, well, is there another shape other than a rectangle that we could use that would be a better approximation? And of course, trapezoid. Okay. So for area of a trapezoid, we have 1/2 the sum of the bases times the height. That's our standard formula. Well, when you're picturing these trapezoids, you have to kind of picture your bases going up and down. So bases in a trapezoid are the two sides that are parallel. So this B1 and B2 are the vertical sides that are parallel. The height of the trapezoid is how far apart your two bases are. So when I go ahead and draw in my partitions here, let's see if I can do any better here. So here's my partitions, breaking it up into 3 trapezoids. The vertical links here, these partitions, are the bases. And the height is just 1, because that's how far apart the bases are from each other. So then if I connect the endpoints with a line segment here, well, okay, that's supposed to be a line segment. Sorry, maybe I need to erase that. Let's try that one more time. Let's see, erase that. Okay, come on. All right, sorry, a little slow. Try drawing that in. Okay, let's start from this one. So if I connect this partition where it hits the function over down to this partition with just a nice line, and same thing over here, connect here down to here with a nice line, and the last one also with a nice line. Not so pretty, but there it is. Try to picture those as 3 trapezoids. So anyway, if I go ahead and factor out the height of 1 for all of the 3 trapezoids, and the 1/2 gets factored out. So here's my first trapezoid, my second trapezoid, my third trapezoid. The 1/2 and the 1 can be pulled out in front. So I just have f of 0 plus f of 1, and then f of 1 plus f of 2, and then f of 2 plus f of 3. So you're going to notice that the first value and the last value doesn't repeat, and everything in the middle does. So you'll get f of 0 is 0, f of 1, well, my function is 1 squared. That happens twice, and then when I plug in 2, 2 squared is 4, and then I plug in 3, 3 squared is 9. So all the ones in the middle repeat, and it's just the ones on the end that happen just once. By the way, when you're looking at it, I'm calling them 3 trapezoids, but actually that very first one, the small one, realistically, it's not a trapezoid, it's a triangle. But you don't even really have to worry about that because f of 0 goes away, and so really I have 1/2 base times height of a triangle, and it all works out okay. Anyway, it comes out 9.5, which is kind of in between our 2 approximations for left and right. So the nice thing about trapezoid is it's actually the average of the left side and the right side. Excuse me. So if I take the answers that I got in the first time, which was 14 and 5, and I average them, I get 9.5. That's what I got for trapezoidal rule. Okay, so I compare that with the actual area. Sorry, I'm coughing here. Hold on a sec. Okay, so if I'm going to compare that with the actual value of the integral, I do my opposite of power rule, and I get x cubed. 1/3, again, you add 1 to the exponent, divide the coefficient by the new exponent. And then I do the second part of the fundamental theorem of calculus. I plug in the top number minus plug in the bottom number. And that should turn out to be 9. And so the actual answer is 9. The actual area under the curve is 9. That compares pretty well with 9.5 from our trapezoidal rule. Okay. Okay, so how much error are we looking at with the trapezoidal rule? We're thinking it's better than the left side or the right side most of the time, but how much error is there? Well, we have a lovely little theorem here where it says error in the trapezoidal rule will be less than or equal to, and then this lovely expression over here. So this is going to be a way that we can calculate the most error that we would end up with using our trapezoidal rule. Error, of course, talking about how much area is underneath the curve. Before we get to that one, I guess looking at the top, it says dealing with the concavity, if our function is going to be concave up, then the trapezoid that we would end up drawing will end up being having too much area compared to the area actually under the curve itself. And then vice versa, if it's a function that's concave down on the interval we're looking at, then when you draw in your side of the trapezoid, the height there, it would be underneath the trapezoid, and the area of our trapezoid would be a little smaller than the area of the actual function. Okay, so keep that in mind. You can tell whether it's too big or too small, our error. All right, so what exactly is all of this stuff in here? Well, the area or the error in the trapezoid is going to be less than or equal to the b minus a. That's the easy part. That's just our interval, a to b. So you plug in your endpoints of the interval. It's always over 12, part of the formula. Your height is going to be basically the same height as the height of your trapezoid. Okay, in other words, how far apart are your partitions? You square it, and then the m with the subscript f double prime, that's probably the hardest part. That's going to be, you have to look at your second derivative, f double prime, and look for the highest or the maximum of value of your function in that interval a to b. So for our problem, we had x squared as our function we were looking at. So if I find the second derivative, it's actually just a constant. And so our constant, the maximum of 2 is just a height of 2. It's a horizontal line at that point, so max is 2. So I plug everything in. A to b, we were on the interval 0 to 3. The partitions were 1 apart, and the maximum of our second derivative is 2. And I compute it all out, I get a half. That actually makes a lot of sense because we said that if I back up, oops, there we go. One more. So when we were doing the trapezoidal rule, we actually got 9.5, and then I compare that to the actual value of the area, and that's 9. So 9.5 versus 9, our error in the trapezoidal rule says at most it'll be a half. That's exactly what it was, 1/2. Okay, Let's see. The last slide here I have for you guys, there's this other way of doing areas approximating called Simpson's rule. And rather than doing rectangles or trapezoids, they use parabolas to approximate it. But we're going to skip that method. I figure enough is enough. Okay, so one practice problem as usual. Give it a try, hit pause, and when you're ready to go, hit play and you'll see the answers. Okay, so here's the answer. We're supposed to be finding the area under the sine wave. So I drew a picture of our sine wave. It said from 0 to pi. Pi, of course, a little more than 3. So here's our picture on the interval 0 to pi. And we're supposed to be breaking it up into 4 trapezoids. So I guess I could have scaled it in terms of pi. That probably would have looked better. But I'll go ahead and approximately draw it in. So if I draw in some partitions, here's one. Another one, and another one. Okay, so here's my 4 partitions, and then I guess I won't draw in the heights. Well, maybe I'll give it a shot. It's going to look kind of messy, but so here's one trapezoid. The next one would go over there, and then this one. Wow, sorry you guys, not looking too pretty. All right, and the last one. So this is supposed to be 4 trapezoids. Lovely. All right, so anyway, they're 1/2 sum of the bases times the height. So the height is basically how far apart your partitions are. So if it goes all the way to pi and we have 4 sections, it's pi over 4 for each of them. So our height, I pulled out in front, pi over 4, the 1/2 from the formula, just sitting out in front. And then the sum of the bases. So for the first trapezoid, it would be sine of 0 and sine of pi over 4. Our second trapezoid, it would be sine of pi over 4 and sine of pi over 2. And then the next trapezoid, sine of pi over 2 plus sine of 3 pi over 4. And the last one would be sine of 3 pi over 4 and sine of pi. And so again, all the ones in the middle repeat, so there's 2 of them. And the ones on the end just occur once. So I add them all up, evaluate what each of those are. It comes out 1.8 or so. And then the question number 2, it says, is that an overestimate or an underestimate? Really hard to tell from my sloppy looking picture here, but when I connect the endpoints to get my edge, the height there for the top part there, it would be underneath my curve. And again, our sine wave is concave down, so it all makes sense. Hopefully area of a trapezoid is going to be an underestimate. And the third one says calculate it exactly. Well, that would be using antiderivative. So opposite of sine gives me cosine, or the antiderivative of sine, I should say, is negative cosine. And I'm going from 0 to 4, 0 to pi, plug in the top number pi, minus plug in the bottom number 0, and I get 2. So if I compare my answer, we knew it was going to be an underestimate, 1.89, a little too small. Actual value, 2. Looks good, makes sense. We are done. Thanks.